All right, let's dive into one of the most exciting corners of artificial intelligence, reinforcement learning. We're talking about how we teach machines to make smart decisions. But here's the catch. We don't give them a rule book. Instead, they have to learn from the consequences of their own actions. So I want you to imagine you're this little robot. You just dropped into a brand new world, a grid, with zero instructions, no manual, no guide, nobody to tell you what's good or bad. Some of these tiles, they might be great. Others, super dangerous, but you have absolutely no idea which is which. So what would you do? How would you figure it all out? Well, you'd have to explore, right? You'd take a step, see what happens, and you'd learn from that. You get a reward? Awesome, that was probably a good move. You fall into a fire pit? Okay, yeah, definitely a bad one. This whole process, this trial and error, that is the absolute heart of what we're talking about today. And that brings us right to our first big idea. What does it really mean to learn without a rule book? Because this is the fundamental challenge that reinforcement learning was built to solve. Okay, so let's break this down. At its core, reinforcement learning, or RL for short, is about an agent, that's our robot, learning how to operate in an environment, which is the grid world. The goal is pretty simple: get the most rewards you possibly can. But, and this is the important part, all of its learning has to come from just trying things out and seeing what happens. There is no instruction booklet. And when I say it doesn't know anything, I mean it starts out completely clueless. It doesn't know the model of the world, which is a fancy way of saying it has no idea what's going to happen when it takes an action. And it doesn't know the reward function, which spots on the board are good and which are bad. It has to figure all of this out by literally just trying stuff. To really get why RL is so special, it helps to compare it to a totally different kind of problem, one where you do have all the rules from the very beginning. This is really the difference between planning something out versus actively learning as you go. So check this out. On the left, you've got offline planning. You might hear this called solving an MDP, a Markov decision process, but don't worry about that. Just think of it like having a perfect, complete map of the world. Every road, every reward, every single probability. You can figure out the best possible route before you even take a single step. But on the right, you have online learning. That's our RL. Here, there's no map. You have to actually go out into the world, explore, and basically draw the map for yourself as you learn from experience. And this slide, it's the perfect example of that known map scenario. This car is living in a world where it knows everything. If it's in the cool state and decides to go fast, it knows there's a 50% chance it stays cool for a +2 reward, and a 50% chance it becomes warm for another +2 reward. Every single outcome is laid out. You could calculate the best strategy without ever leaving your chair. But what happens when we take that map away? Now you're not just a planner anymore, you're an explorer. You have to figure out how to act in a world that you just don't understand yet. And it turns out there are two main ways to approach this problem. The first strategy is pretty intuitive, right? If you don't have a map, well, why not just try to build one? This whole idea is known as model-based learning. You can think of this as the scientist approach. First, our agent just wanders around, trying things and carefully taking notes on what happens. Okay, when I did this action in this state, I ended up over here and got this reward, over and over again. After a while, it uses all those experiences to build a pretty good guess of what the map looks like. And once it's confident that its map is good enough, it stops exploring and just uses that map to figure out the best path, just like in that easy offline problem we saw before. But, there's another way to do this, an approach that's often way more direct and a lot more efficient. And that brings us to strategy number 2, learning by doing. The big idea here is, what if we could just skip the whole map-making part entirely? This is what I like to call the pragmatist's approach. It basically says, look, building a perfect map of the whole world, that's a ton of work. Let's just focus on figuring out what actions are good and what actions are bad in any given situation. It's all about learning the value of things directly. Now, the simplest way you could possibly do this is called direct evaluation. The idea is super basic. Every time you visit a state, you just keep a running tally of the total reward you got from that point all the way to the end. Then, you just average those totals for each state. So a state that always leads to good things will naturally get a high value. Simple enough, right? But what's really interesting here is the question this slide asks, because it points out a huge flaw in this simple approach. Think about it. If you have two different states, say B and E, and from both of them your strategy is to go to state C, well, you'd think their values would be related, right? But direct evaluation learns the value of every single state completely on its own. It wastes all of that juicy information about how the states are connected, and that means it can take a really, really long time to learn anything useful. And the solution to this problem is it's an elegant and super powerful idea called temporal difference learning, or TD learning. Instead of waiting for the whole game to be over to update your values, you update your guess after every single step. You take an action, you see the immediate reward and where you end up, and you just nudge your value estimate for where you were to be a little bit closer to the reward you just got, plus the value of where you landed. So the crucial point here is that TD learning is basically like keeping a running average. It learns from every single experience, and that lets information flow between all the connected states. An agent doesn't need to fall into that pit 10 times from state B to learn B is bad. No, it just needs to learn that B leads to C and C leads to the pit. The badness of the pit works its way backwards, which makes learning so much faster. It's a game changer. Okay, so we've figured out how to efficiently learn the value of just being in a certain place. But honestly, that's only half the battle. How does our little agent actually use that information to decide what to do next? And this slide just illustrates that final leap in logic perfectly. On the left, we were learning what we call v-values, where v stands for the value of a state or a location. You're asking, how good is it to be right here? But on the right, we shift to learning q-values. You can think of Q as standing for the quality of taking a specific action from that state. So now you're asking, how good is it to go north from here? It's a subtle change, but it's a profound one. This brings us to the big one. Q learning. It's a model-free technique, and it uses that same super efficient TD update rule, but instead of learning the value of a state, it learns the quality, the Q value, of every possible action in every state. By doing this, the agent doesn't need a map anymore to decide what to do. To pick the best action, it just looks at all the Q values for where it is right now and picks the one with the highest number. It's really that simple. So why does any of this matter? Who cares about little robots in grid worlds? Well, because these exact ideas, scaled way, way up, are what power some of the most mind-blowing achievements in AI today. This is the foundation for teaching an AI to play incredibly complex games like Go better than any human. It's how we train robots to walk and pick up objects, and it's used to optimize unbelievably complex systems in logistics, finance, you name it. Which really leaves us with one final thought. We've just gone through the basic strategies a machine can use to learn from absolute scratch, just by messing around with its world and seeing what happens. It really makes you wonder, right? What could a machine that truly learns from experience accomplish next?